to have a workshop on resurgence and localization in string theory going on right now, and we asked one of the organizers, Gerald Dunne, to give us a simple introduction into the subject. So if it's too simple, please blame me. I asked Gerald to be as broad and simple as possible, but if it's too difficult, blame me.
Okay. Okay, where do I begin? Okay, thanks, Sasha. And let me begin by thanking the Simon Center for hosting this workshop. It's a very interesting example to bring together people from very different areas on some common theme. So I want to talk at a fairly general level about what this strange word resurgence is and this concept of trend series. And I'll make reference to various talks at the workshop, so if you're interested, you can come along. So the original physical motivation, let me list some physics motivation before I get to the mathematical ones. There's this relatively recent development about improving asymptotics beyond the sort of traditional classical asymptotics of Poincare. And the idea is to see if it's relevant and useful in quantum field theory and string theory and integrable models. The original motivation that I had was actually a problem with Mittat on understanding the infrared renormalon puzzle in asymptotically free quantum field theories. This is really a very difficult problem. And that's how we came to first try to work on resurgence in field theory. There's also another long-standing problem that has puzzled me for many, many years, is there are systems that have non-perturbative physics related to asymptotic perturbative expansions, but they have no instantons. And it's not totally clear yet how to handle these situations. And a fourth motivation, we heard a really wonderful talk this morning from Sergei Lukyanov, which touched on this really deep relation between integral models and actually even deformations of integral models that have some very deep underlying structure that can be translated into relatively simple differential equations. It's really remarkable in my mind. And a lot of the mathematics that's been developed by mathematicians for resurgence is in the language of ODEs, of course, not in the language of quantum field theory. So if one is to learn how to apply resurgent techniques to quantum field theory, this is, I think, one avenue that is particularly powerful. But there's actually a bigger picture behind this. These are now very ambitious things to try and actually use the concept of a trend series, which I haven't defined yet, I'm sorry, to actually give a non-perturbative definition of quantum field theories, non-trivial quantum field theories, not via the lattice, but really in the continuum. An aspect of this is to try and understand what it means to do analytic continuation of path integrals. It's a formal statement. And it's only recently that people have been trying to really implement that both numerically and analytically. And here the word Lefschetz thimbles, I'll touch on that later to try and explain at least the motivation. It's still not very well understood. And something that I'm particularly interested in is that if you were able to understand analytic continuation of path integrals, then you would free yourself from the problem of the lattice being stuck with Euclidean path integrals, which limits the type of problems, physics problems, that the lattice can address. If you really could understand, by understand I mean understand at the level where you could actually calculate something from the path integral, for Minkowski path integrals, you would have access to non-equilibrium dynamical processes in field theories. So this is really an ambitious topic, but it's worth keeping something like that in mind. So the mathematical motivation, so on the time scale of mathematics, resurgence is a relatively new idea. The term was coined by Carl in 1980, but the ideas can really be traced back to some beautiful work by Stokes trying to understand rainbows back in the 1850s. And Stokes had this brilliant insight related to the Airy function that we all know, that on one side the Airy function is governed by one exponential, and on the other side is governed by two exponentials. It's oscillatory. And he was trying to understand how this could possibly work. And in doing so, he developed a lot of the language and ideas of Stokes phenomena, Stokes jumps, which are absolutely crucial for implementation of resurgence. So in broad terms, whoops, that's the wrong one. In broad terms, resurgence is some sort of unification of perturbation theory and non-perturbative physics. So those are just words. I have to try and convince you that these are meaningful words, what it means to unify and what you gain from it. So the starting point is that, as we all know, that in interesting field theories or even in interesting quantum mechanical systems, perturbation theory generically leads to divergent asymptotic series. But of course, we also know that this is not a problem. This is not a bad thing. It just means we have to understand how to extract mathematically sensible and physically sensible information from these series. So the first step in the process of defining resurgence is to replace an asymptotic series expansion by something called a trans series, which I will define on the next slide. And as a first hint, one of the things you can think of is that this trans series is an improvement of an ordinary perturbative series in the sense that it's built to contain the analytic continuation information for the function. You'll know that if you have an asymptotic expansion of a function along a particular line, it does not contain enough information to describe the function in some region in the complex plane. The goal of a trans series is to have that information encoded, so that in some real sense, if you have the trans series in some region in the complex plane, where it exists, it really is the function, whereas an ordinary asymptotic series is not the function. Okay, so that's a goal to keep in mind. And a consequence of this is that
the series doesn't diverge.
I'll give you examples as we go along. Just keep it in mind as a goal. So a consequence of this is that perturbation theory and non-perturbative expansions get intricately entwined in interesting ways. If you can learn how to disentangle that, you can actually gain non-perturbative information from perturbation theory and vice versa. So that's the sort of big picture of where this is going. It's been developed to in great detail in mathematics in differential equations, both linear and nonlinear. And the next talk this afternoon by Ovidio Costin will be about the development of this for nonlinear differential equations, with particularly the Penlevet systems, and they show up everywhere in physics. So knowing and understanding the asymptotics of the Penlevet systems is a very deep and important problem. It's also been applied in fluid problems and in more physics, particle physics or field theory contexts, in quantum mechanical models, matrix models, and field theory and string theory. And there's also a little bit of a philosophical shift that I went through. When I was a student, I was sort of taught that semi-classics or asymptotics was really just an approximation which might be useful somewhere in some particular region. But there's an idea here that it may actually be exact in some sense that I hope to explain as I go through. Okay, so the first step is, what is a trans series? So this is not the most general trans series to a mathematician, but this is the form of trans series that seem to appear in physics problems that we've come across so far. You replace the series of perturbative fluctuations, g squared will be my small parameter, with, instead of just one series, a triple series. A series over perturbative fluctuations around instanton sectors, e to the minus some constant over g squared, but also powers of logarithms of the coupling.
Convenient to call it free waves.
Call it what?
Based on free waves. There are three basic elements on which you did experiment.
Okay, they're called transmonomial elements. Okay. So, okay. So Ekal was actually studying a totally different problem, nothing to do with directly anything to do with quantum mechanics or field theory. And he asked a very abstract question of, is there a set of functions that's closed under these three operations of Borel transforms, analytic continuation, and basically inverse Borel transforms, Laplace transforms. And surprisingly to me, there is an answer that you can basically build these out of just these three elements. Now, when I said this wasn't the most general trans series, the most general trans series can have iterations, e to the, e to the, e to the, e to the, log to the log, etc. But these are the form, I say here in physics, this seems to be a fairly general form that shows up. So people who know field theory will, of course, recognize this and just say, oh, this is just multi-instanton calculus. We recognize each of these guys. This is perturbation theory, this is instantons, and these are quasi-zero mode integrals coming from the interaction between instantons and anti-instantons. So it's a...
Run with the coupling. I mean, there's a run.
Okay. We'll get to that. Okay. I'm giving the mathematics definition here. Okay. So it's a reasonable question to ask, is there anything new? Is this just a renaming, fancy words for something that field theory people already know? And I think there are three answers to that. One is that this concept of analytic continuation being encoded in this trans series, and also that these coefficients are not random. There are very, very strong relations between these coefficients. You can roughly speaking think of this as expansions in three directions: the perturbative direction, the instanton direction, and the log direction. And so the coefficients have three indices, but they're not independent of one another. They're extremely tight constraints between the expansions in the various directions. Okay, so it's not 3 times as difficult a problem. And also there's this concept that you can actually get exponentially improved asymptotics, where instead of just dropping all exponentially small terms, you can actually keep them consistently in such a way that when you analytically continue and they come back to being of a reasonable size, they're still there. And this was the Stokes idea. So this is particularly important in some field theory problems where you might have some external parameter like a temperature or a chemical potential, and you need or want to be able to analytically continue in that parameter, rather than just having an asymptotic expansion. Having a trans series representation contains a lot more information. All right, now, so that's trans series. Now, where does the word resurgence come from? So this is a quote from Ekal's work that resurgent functions display at each of their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or surge up in a slightly different guise, as it were, at their singularity. So what does that mean? So I'd like you to try and remember this sort of picture. These dots are some sort of critical points, saddle points, special points in whatever problem you're thinking of. And you might be interested in the fluctuations around these particular critical points or singular points or saddle points or whatever they are. And the idea of resurgence is that the fluctuations around these points are not independent of one another, and in fact, under certain circumstances, are so closely tied together that if you know the fluctuations around one region in very great detail, you can extract the fluctuations around other saddle points precisely. And I'll show you some actual examples where this works. Okay? So, but this is the extreme idea of resurgence, and there's no guarantee that this should apply to quantum field theory problems, in particular the problem that Ismail mentioned. So far I haven't mentioned anything about running of G squared, right? So we have to keep that in mind as we go along. And roughly speaking, to me, it's still very surprising that doing this sort of local analysis around critical points contains a lot more information than you might have thought. And so I want to try and convince you by examples, because I can't prove any of this. So let me begin with what I think is hopefully a familiar problem. And this was the first hint of resurgence, I think, in the standard physics literature. Think of the quantum mechanics problem with a double well or a periodic potential. So everybody knows that the energy levels are split, and that the splitting at first order is given by the single instanton. It's some exponentially small splitting. S, depending on the problem, is sort of the instanton size in some units. It's usually here 1/6, here 1/2 in some canonical choice of parameterization. And this is the standard textbook example in every introduction to instantons that has ever been written. But they sort of stop just when it gets interesting, because the next step is that if you were to do perturbation theory about one of these isolated wells, you would discover that perturbation theory is, of course, divergent. That's not a surprise. What's more surprising is that it's non-alternating. It's going like n factorial, but not alternating. So formally speaking, it's not Borel summable. And moreover, the size of the growth is twice the single instanton action, not the single instanton action. And so this means that if you take the Borel summation story literally, you would imagine that imagine. You would expect that you induce from this Birrell summation some imaginary part to the energy, which is exponentially small. But of course, that's ridiculous, because in these systems, they're completely stable, nothing's decaying, in contrast to, say, the cubic oscillator problem, where there's obviously a decay and there's obviously an imaginary part. In these cases, these are perfectly stable. So this imaginary part shouldn't be there. Moreover, it's ambiguous. And moreover, it's related to a two-instanton effect, not a single-instanton effect. Okay.
A renormalon just because it's a different singularity?
It's not a renormalon yet. This is a quantum mechanics analog of a renormalon. I'll get to the renormalon story in a little bit. Okay, but it's the most precise analog of that problem. So Bogomolny and Zingerstan and also Parisi and Berzan, these people were worrying about this problem at the end of the 70s, and eventually they came to the brilliant resolution, which is that if you think of perturbation theory, there's this non-Borel summability problem, which induces this ambiguous imaginary non-perturbative term. But they also realize that if you do the standard non-perturbative analysis, which we call the dilute instanton gas, if you do it to first order, you get the splitting, and that's unambiguous. But if you look at the next order, you have to now worry about instanton-instanton interactions. And there's interaction between instanton and instanton, anti-instanton and anti-instanton, but there's also between instanton and anti-instanton. And this is actually unstable, because these guys are trapped. And so formally speaking, it just ruins the whole picture of a dilute instanton gas. And they realized that this could be controlled and stabilized, if you like, by analytically continuing in the coupling G squared. They actually took it to minus G squared. That's actually not necessary and not even correct. All you have to do is take it off the positive real axis, stabilizes the problem, but you can do that two ways. You can go like this and come back, or you can go like this and come back. And they realized that if you do this in this instanton gas picture, because of the attraction between instanton and anti-instantons, you generate an imaginary part, which is also ambiguous, and it's exactly the same imaginary go. And they noted that with an appropriate choice of conventions for signs, these two would cancel exactly. Okay, so this is the first hint of what I would call resurgence, that a perturbative computation on its own is incomplete and ill-defined. A non-perturbative computation on its own is ill-defined and incomplete. If you happen to do them on the same piece of paper, then they can actually cancel, and you get a unique, well-defined, real answer, unambiguous to the problem you're trying to calculate. Okay? So this, I think, was the first hint of resurgence, and the statement of resurgence is that this should happen to all orders in the multi-instanton expansion. This is just the tip of the iceberg. And so there's some very, very complicated way that this must be implemented in the all-instanton type expansion at higher orders. Okay. So that's, I think, the cleanest example. I'll come back to that example in a lot of detail later, if I ever get to it. So now coming to George's question, that was quantum mechanics. The reason there's divergence of perturbation theory in quantum mechanics is essentially combinatorial, just that the number of diagrams grows factorially. But now, if you go to quantum field theory, there is also a combinatorial growth of the number of diagrams. So there are also instanton type effects. But there's a new type of effect, which is from the running of the couplings. And it turns out this effect is stronger in the sense that the rate of growth that it induces is faster. And the rate of growth is associated with the location in the Borel plane of the poles or cuts. And so these correspond to cases where these Borel poles, or generically branch points, will be closer to the origin, and so they lead to larger non-perturbative effects. So in that sense, they're more important than the combinatorial growth coming from instantons. Yep.
Any sense in which that's true outside of the large n limit, or is that kind of only parametrically a large n statement?
No, that's true outside of the large n limit.
But so for SU2 Yang-Mills, for instance, like the renormalons and instantons are comparable?
So renormal singularity is 8 times closer to the origin than the instanton anti-instanton singularity.
So it's really literally 8?
Yeah.
No, it's 4 times.
4 times n or something.
11 thirds.
Okay, but
So,
that parametrically is not just a large n approximation.
Right, that's exact.
There are closer singularities.
All right, so here's a picture. So now let me tell you what this puzzle is. is that if you do perturbation theory, because of these renormalons and because of the rate of growth being faster, and it's non-Borel summable because of these infrared renormalons, you would induce imaginary non-perturbative terms that look like this. It's e to the minus twice the single instanton action, but divided by beta 0, which is the leading beta function coefficient. So parametrically it scales with n. Okay? Whereas if you look at instantons on, say, R2 if you're doing CPN or something, or R4 if you're doing Yang-Mills, the exponential things that you would generate from instanton anti-instanton look like this. So clearly the exponents don't match, so it looks like these things don't correspond to one another, and that this Bogomolny-Zingerstein mechanism from quantum mechanics is not the resolution and combination of a trans-series form. And basically this means that the instanton anti-instanton poles that are coming from combinatorics and these renormalon poles aren't in the same place, so this cancellation doesn't happen. Okay, however, there's a recent developments, partly work by Philip and Mittat, and then myself and Mittat in the CPN model, is that there's another problem when you go to field theory for this instanton gas picture, which is that there's a scale invariance issue with instantons. They have the scale modulus problem, and you have to control that before you can do a serious calculation. And so if you control that, there are ways to control it. And what we showed in the CPN case is you control it by a spatial compactification, and this will be discussed later in the conference by Alexei. And when you do this, you discover that, in fact, there are new non-perturbative objects for which the Borel poles lie exactly on the location of the infrared renormalon poles, and the cancellation occurs. So let me tell you what I mean by cancellation, but I'm not going to give any more details than this for lack of time. The spatial compactification and this principle of continuity generates Zn twisted boundary conditions, and the instantons fractionalize. They fractionalize according to n. This is in CPN minus 1, and n is actually just beta 0. So the basic non-perturbative objects have exponential form e to the minus s over n, not e to the minus s. And now if you build your non-perturbative analysis on these basic objects, you can calculate the amplitude corresponding to one of these objects, instanton, anti-instanton, with particular alignments, and you discover that the ambiguous imaginary part has this exponential and this prefactor, and that if you go and compare with what happens in the perturbative sector, it's exactly the same. The exponent's the same, the prefactor's the same. So this is, again, the leading tip of the iceberg of the Bogomolny-Zingerstein cancellation in this non-trivial two-dimensional asymptotically free quantum field theory. Unfortunately, we don't know how to go to all orders in these cases. We'll have to reserve that discussion for quantum mechanics now. Okay, so that's one application in field theory, but now I want to change gears a little bit and just ask the question, where is this coming from? Should we expect it to apply in what level of generality? And I'll talk a little bit about some quantum mechanical examples and then come back to field theory later on. So let's look at these paradigm cases of double well and periodic potential a little bit more closely. And we'll use uniform WKB. The idea is the following. When this parameter g is small, this barrier goes like 1 over g squared, so the barrier is very high. The separation goes like 1 over g, so they're very far apart. So if we're looking, say, at energy levels inside the well, because the barrier is becoming very high. And it's no big surprise that the non-perturbative effects will go like e to the minus some constant over g squared. But in this limit where g is small, the basic problem around one of the wells is harmonic. Okay? These are degenerate harmonic vacua when g goes to 0. So if you're going to do WKB, you shouldn't just mess around with usual WKB. You should just do it properly and use what's called uniform WKB. You write the wave function as it should look. So you write it as a solution of the harmonic problem, because it's a harmonic problem. So you write it as a parabolic cylinder function. If you do this, you don't have to worry about these usual problems about singularities at turning points. This is completely regular, completely smooth, all the way through turning points. Okay, so that's the idea of uniform WKB. So now what I've done is I've traded the wave function, if you like, for another function u, and I'm just going to do perturbation theory in u instead of perturbation theory in psi. Okay? Now, if you're paying attention, you will have noticed that I snuck in a new parameter, nu, into the problem, and this is going to play the role of the label of the level number, the level that is being perturbed. Okay? It doesn't appear in the original differential equation, but when I make this change of function, nu will appear in the equation, obviously. So what happens? Well, you just close your eyes and do perturbation theory in the normal way, and you generate an expression for the energy, which is a series in g squared, and the coefficients obviously depend on nu. And if you think about it for a little bit, you realize that they're just polynomials. They're polynomials of degree k, or maybe k minus 1, I don't remember, of order k, in this parameter nu. And it's completely routine. You just generate perturbation theory. If you then take nu to be an integer, then this expansion is exactly perturbation theory. Really Schrödinger perturbation theory. So there's this misconception out there that WKB only gives you information about the spectrum high up. That's completely wrong. You can do perturbation theory even down near the low levels using WKB. Okay? And this is the way to do it. And I'll make it much more explicit as we go along. But now this cannot be the whole story, obviously, because this is just perturbation theory in one. Well, I haven't given you enough information to solve the problem, so it's no big surprise that this thing is non-Borel summable for a given nu. You shouldn't be surprised by that because I didn't define the whole problem. So now I have to define the whole problem and tell you the real boundary conditions. And so in the double well, I'll take the symmetric double well because it's technically a little bit simpler. The boundary condition is just the wave functions have parity. They're either even or odd functions. So the derivative or the wave function itself must vanish at the midpoint. Clearly, that's a condition, but it's not contained in perturbation theory. Or here I have some block boundary condition from just the form of the potential. And now you see the problem. The problem is, since these expansions and also the corresponding expansions for u are non-Borel summable, to make sense of them, I must continue g squared off the positive real axis. I don't have to go very far. I have to just go off the axis. But now what that means is that my parabolic cylinder function is defined at a large but complex variable. Okay? And so the boundary condition is not that this thing be normalizable. The boundary condition is that this thing, say, vanish at the midpoint. Okay? And so now we just go look up a book with the analytic properties of the parabolic cylinder function, and it looks something like this. There are two terms. There are two exponentials. One's decaying and one's growing. Normally, we say that we kill this guy because it's not normalizable. How do we get rid of it? We get rid of it by taking u to be an integer. That's the quantization condition for the harmonic oscillator. Okay?
What is the second?
The second one's already been taken care of in this direction in perturbation theory.
Well, you said it was not normalizable anymore when you went complex.
What I'm saying is I don't need it to be normalizable in this direction. The appropriate boundary condition is just that it vanished.
That is one.
Yeah.
The other is
The other is The other is taken care of in doing perturbation theory by having it decaying in that direction.
But then there's also this issue of self-adjointness.
It doesn't matter. Don't worry. I mean, you know everything about these parabolic cylinders. So
But you know the answer in this case. But what if you didn't know the answer?
No, but you know it's approximately harmonic. Okay, so end of discussion. So now let's consider the case where the boundary condition is that the thing vanish at the midpoint. So you just have to balance this term against this term, and you see that you collect the exponentials together. Z is at the midpoint, so it's roughly of order 1 over g. And so you collect that guy here, and then there's a root pi, there's a 1 over this gamma, there's some powers of g coming from this one, and then there are some sort of fluctuation things that I'll put into this function p. So this is the single instanton factor. These are the fluctuations around the single instanton. If g was 0, this has to be 0, and the way you make it 0 is by taking u to be an integer. But if g is not exactly 0, this is just small, and the way you make the left-hand side small is you take nu to be close to an integer. So it's completely straightforward. You just expand both sides near an integer. All you're using is the properties of this parabolic cylinder function. and you get that nu is an integer plus a series in this single instanton parameter xi, and with some powers and some functions. And at second order, you see some logs, and the logs are just coming from this guy. And that's the origin of the logs in the trans series. This is nu. I just plug it back into my formal series. Since these are polynomials, there are no problems, and I see that I have a triple expansion in powers of g squared, powers of this exponential, and powers of logarithms. Okay? It's extremely simple procedure, and it agrees with all the other ways of deriving things, and it's much cleaner because I don't have to pick some convention about choosing my signs. It's all built into the asymptotic behavior of the parabolic cylinder functions.
Logs uniformly bounded?
I don't even know what that means.
They are bounded by a fixed amount.
What do you mean? I don't know.
The logs do not, it's not a triple graded trans series. Logs can appear only up to a fixed power.
Yeah.
Oh, because that's at a given instanton order, so there's only a certain amount of interaction between a certain number of instantons. So physically, it's completely clear. Okay. All right, so that's the origin of a trans series. So there's a conjecture due to Zingerstein and Genshure that in fact, you only need two things to generate the entire trans series. So this is going back to this idea of Ekal that if you know something about the fluctuations, you can generate everything else. So it looks like you only need to know the perturbative expansion, perturbation theory, and this fluctuation function. Everything else is built out of these two objects. So that's a very strong statement. This is a very strong conjecture. And at the level of the rigor that I've just given you, we have an explanation or a proof of that using uniform WKB. It's completely straightforward where that comes from. But the story is actually much more interesting than that. You can actually look, treating the problem this way reveals this surprising fact that in fact, you don't need these two functions. You only need one. If you give me perturbation theory, E of n of g squared, this is just straightforward perturbation theory, I can write down in one line the fluctuation around the single instanton. Here's the explicit formula. I just have to differentiate with respect to this and change some powers by doing the integral. Okay? I'll give you a two-line proof later. Okay?
No, it's not proof. Meaning. Why is this?
Comment, and you guys explained what the meaning was. I'll show. Okay. So this is quite dramatic. This says that actually everything about the trans series is in a complicated way encoded just in this function. Okay? This is very surprising. And so one of the points I want to make later, if I get to it, is that, and I think it bridges a connection with some of the other talks in this workshop, is that if you look at this in the language of Nikita's partition function, you should be surprised that there's a connection at this point. It's totally clear why this is true. Okay, so I'll come to that later. So let's test this. And so I'm not going to test it. These gentlemen here tested it. So the prediction is that if I know the fluctuations around the perturbative vacuum, I can now write down the fluctuations around the instanton sector or the two instanton sector or whatever you want. I can write them down. You ask for it to 27 orders. All I need is perturbation theory to 27 orders. Okay, it's a constructive correspondence. So these gentlemen just did a heroic calculation in the double well case of calculating the fluctuations around the single instanton in the double well the way you would do it in field theory. So diagrammatically. So there are all these three-loop diagrams. They did some hard work. This was a calculation by Edward some years ago. In this case, they weren't able to do it all analytically. Some of the diagrams were calculated numerically, and this is the number. Okay? Now I take that formula on the previous page, I input perturbation theory into that formula, and Resurgence tells me that this should be this, where n is the level number. This calculation was done for n equals 0, the ground state. And you see this number, believe it or not, agrees with this to 4 or 5 decimal places. Okay? So this is what I mean that Resurgence could actually be useful. This is a very difficult calculation. to do fluctuations. You're calculating three-loop diagrams using propagators that are propagators in the background of an instanton. This is really, I'm amazed. You guys are incredible. You're able to do this. Right? This is a very difficult calculation, and yet it's completely encoded in perturbation theory somehow. And I think that deserves to be understood in detail. Okay? And I've just been told that they repeated it for the Matthew case, and it also agrees to some number of decimal places. Okay? And there's more, because this is known for any level. And again, as I said, it's constructive. If you want it to some number of orders, I can give it to you to the same number of orders that you give me perturbation theory. Okay? Yeah.
At some point we report here that this finite action solutions and so on.
Yeah.
We want to imagine that this works also for solitons or monopoles or something.
No, these have to be finite action solutions. All right, so this is, if I draw this picture again, I didn't believe this claim of the mathematicians that if I knew everything about fluctuations around the perturbative vacuum, that contained all the information. I just simply didn't believe it. And Zingerstan's result gets close, but in fact, it really is true in some very complicated way that the fluctuations around all the other multi-instanton saddles are indeed explicitly encoded in perturbation theory, the fluctuations around this trivial saddle. Okay, so why? Let's, we're talking now about differential equations. We want to eventually get to field theory, so we'd like to understand this maybe in the language of path integrals. So let me give you another perspective on resurgence. There are many ways resurgence was sort of rediscovered or developed by different branches of mathematics and mathematical physics independently. They're all sort of coming together now. Let me give you another version, which came from work by Michael Berry and Chris Howells. They were studying something called hyperasymptotics, but that's not important. For this discussion, what is important for this discussion is that they realized something quite deep about all order steepest descents. So imagine the following problem in 0 dimensions. Imagine you have some function with a certain number of critical points, and you do some contour integrals through a given critical point. So I'll label the critical point by some number n. And so this is some contour going through critical point n, and that's some function of g squared. Okay? So the normal thing we learn in textbooks is we find the critical points, we find the steepest descent contour. The dominant exponential is just a function evaluated at the critical point. There's some Gaussian fluctuation piece, which is a prefactor. And normally we say, okay, we stop there. Okay? So Berry and Howells asked the question, well, what if you don't stop there? What if you keep going? So if you keep going, you're going to get a fluctuation around this, which is a series in g squared with some coefficients here. Okay? So simple problem. Something very interesting happens. So using really elementary juggling of contours and deforming contours, you can prove that the fluctuations around saddle point number n is exactly related to an integral transform of the fluctuations around saddle point m, where I'm summing over m, and these are saddles that are somehow connected to. So there's a very interesting topology there that I don't want to get into details, but I can tell people about it later. This is an explicit relation between these fluctuations, and capital Fnm is the difference of the actions at these two saddle points. Okay, so it's the magnitude of the difference of the two exponents. Now, the reason this is interesting is that g squared now appears here, so I can formally expand in g squared, and you get a relation between the coefficients of, in this expansion, around saddle point number n, and the coefficients around saddle point m. Okay? And you learn that the basic growth is factorial. That's the power that goes with the factorial is the difference of the exponents, inverse of the difference of the exponents. And the overall numerical coefficient is the 0th coefficient around saddle point m. And then the subleading behavior involves the next coefficient around saddle point m, and so on. Okay? So let's see how this works. And this is in this language, it's basically some form of double theorem that the fluctuations around some singular point are governed by the fluctuations around some nearest singular point. So let's see how this works in some simple examples. Here's a... Yep.
Is this sum convergent or is it?
This is a formal expansion. I can write it in a it's an asymptotic.
It's not equal.
Okay.
No, I mean.
Okay, yeah. Let me show you on the next slide. I'll show you an explicit example. It should be a asymptotic. So here's a simple example where we have a zero-dimensional partition function for a periodic potential. Clearly this integral, which by the way is just some Bessel function, has a saddle point at 0 and a saddle point at pi/2. This one's a minimum, this one's a saddle. Obvious. Okay, so you can just write the integral, or you can evaluate at the two saddle points. And at the one at the origin, the coefficients of the expansion are just some gamma functions. And so the asymptotic behavior at this at large R is just this with some coefficients. Okay, I should have written that tilde on the previous. Okay, now we look at the expansion around the other saddle point. And they're just the same numbers. Okay? And I can go to as many orders as you want. Okay, so this is a statement that there's really a quantitative relation between the fluctuations around some particular saddle and around another. But this is for zero-dimensional contour integrals and one-dimensional contour integrals. Even if you go to two-dimensional contour integrals, C2, this story becomes very complicated, very non-trivial topology. And this goes under the name of Picard-Lefschetz theory and was studied by various people. And once you see how complicated that is, you would think this could never possibly work for a path integral. Okay, so suppose you ignore that for a second and just do a calculation. Let's go to quantum mechanics, so functional integrals. And let's not do this zero-dimensional integral. Here, let's do the path integral for the sine squared problem. And here are the fluctuations around the perturbative saddle. So this is perturbation theory. The leading growth is factorial. The sub-leading growth have some coefficients. And now you go do a different calculation in the instanton, anti-instanton sector. And these are the numbers that you get from the fluctuations around that. Same numbers. Okay, now you do it for the double well, same numbers. Okay, so these are spectacularly difficult calculations, and these are spectacularly simple. Okay, so that's the sort of idea that maybe if we can understand in more detail how this works, and maybe eventually in some types of quantum field theories, this could be useful and interesting. So there are various branches of physics now that are trying to implement this in many different cases. At this point, it's not very well understood or very well developed. And the name is the Lefschetz symbol, and the motivation is the following. So suppose you're doing finite density QCD. You try to use lattice QCD, and you use Monte Carlo. You try to do that at finite density, and you're immediately finished. Because the measure is complex. You cannot do your standard Monte Carlo routines to define finite density QCD. Okay, so the people have been trying to develop ways around this, but it's an absolutely fundamental problem, not just in QCD, in many branches of physics. This is well known as the sign problem. So an idea hasn't been implemented successfully very well. Hold on. But an idea is the following. Suppose you understood what it meant to deform the contour of the functional integral to a steepest descent contour. Suppose you understood what those words meant. What that means is you've deformed the contour to a case where the action has a constant imaginary part. That's the definition of the steepest descent contour. Once you've done that, you can take the imaginary part outside of the integral. You're left with a real, and it turns out it's monotonic measure. You can now do semi-classics, Monte Carlo, Langevin, whatever you want. Okay? So this has not been successfully implemented yet, but it's a clever idea and it's worthy of consideration. We heard a very nice talk yesterday by Stavros about actually trying to do this in Chern-Simons theory, where you can really do these calculations. He didn't phrase it in this language, but this would be a case where you might actually be able to make some of these statements precise. Okay. All right, so resurgence would add another level of interest to this, is that there will in general be many of these so-called thimbles, because there are many critical points. And the statement of resurgence is that the expansions around these various thimbles would not be independent of one another, would be related to one another. So this could, just at a pragmatic level, it could provide numerical checks that these thimble expansions make sense. All right, there's a lot of interesting mathematics here that's not well understood. I'm running short of time, so I'll skip through this. The idea is to use gradient flow in the complexified field space to generate these thimbles through these saddle points. So this has been studied in Chern-Simons theories. It's been compared with complex Langevin in simplified examples. There's one working calculation which uses a very severe truncation, in the sense that it only looks at the thimble through the trivial vacuum for the Bose gas problem, which has a sign problem. They did this numerically. This is the Aurora group in Italy. It's a lattice group. And they got results that actually agree with an independent calculation in the...
Tomorrow is the Tokyo day.
Fantastic. So I urge you to go to the seminar tomorrow. But this is very early days. I mean, this is not understood in complicated field theories, but I think it's a very good idea, and it deserves consideration. And resurgence gives you some sort of hope that it might actually work. So here's an example where we can actually understand some of these complex instantons and complex thimbles. Just replace the periodic potential, the cosine guy, by an elliptic function. Okay, seems fairly innocent. And if you just do the standard Bender-Wu, Lapatov type story that I was telling you before, you would predict that there's an instanton tunneling from one well to another. You calculate that instanton action, and the rate of growth of perturbation theory will be n factorial divided by twice that instanton to the power. Okay, it's a standard prediction of the story I've been telling you so far. So we calculated the first 30 coefficients, and it doesn't work. It fails very badly. And the reason it fails very badly, we didn't randomly stumble on this example, is that this example is doubly periodic in the complex plane, okay, unlike the cosine potential. And so actually, there's a complex instanton in the complex direction. But your original path integral was over real paths, so you say, well, I don't care about that complex. But the philosophy of steepest descent contours is that analysis is that you should consider all saddles, not just the real ones on your original contour. And this is an example. If you include now the contribution of this complex tunneling in the other direction, suddenly the asymptotics matches perfectly. Okay? So we didn't solve this problem using the thimble, but we solved this problem by incorporating the contribution of another obvious complex saddle point in the path integral, and now it matches with perturbation theory. And if you ignore them, it doesn't work. Okay, so there's a very explicit demonstration that you need to at least consider these guys in doing these analyses. Okay, I don't really have a lot of time for this, so let me just say that somebody should have put up their hand by now and said this is all nonsense, because there are models like ON models where there are no instantons. And yet there are these problems with perturbation theory. And it turns out that this is also a feature of Yang-Mills theory in CPM, that they're actually finite action non-BPS solutions. So these are bona fide saddles in the path integral. And if you're going to tell me that you're going to do a serious saddle point analysis of these path integrals for these theories, you have to tell me either that I should consider these saddles or that I shouldn't. They're saddles, they have finite action. They're either connected to the other saddles or they're not. It's a very difficult problem, but they need to be considered. So what could they possibly mean? They were systematically ignored by physicists because it was known that these saddles had unstable modes. You look at the fluctuation problem around them, and there are some negative directions. Therefore, they were sort of neglected as, I don't know what they are, so we'll ignore them. In the language of this resurgence, we should revisit this problem and really think about what these things are and what they mean. And so a possible rationale for considering these is that in these theories, where there are no instantons, these unstable finite action saddles are actually playing the role of the instanton anti-instantons, and the fact that there are negative modes are giving you imaginary contributions from the saddle point analysis which can match the Borel. And this was actually demonstrated explicitly in the principal chiral model, which also is in this case. And I get, Alexei, you'll talk about that? Okay, on Friday. Okay?
All sphalerons, right?
They're not sphalerons.
They're not sphalerons.
No, they're not sphalerons. This is Euclidean. They're sphalerons in one dimension higher, but they're not sphalerons in the Euclidean. Okay, so let me now continue. Okay, Nikki, yeah.
So if the number of negative modes is even,
Yeah. Nobody knows. No,
just there is a very trivial example, the two-dimensional angles theory, where
yeah.
perturbation theory is finite, and there are these saddle points which have always even number of negative modes, so they're all actually important. You sum all of them to get the full result.
Yeah.
So there is no Borel summability issue, but
and perturbation theory truncates in that. Yeah. Yeah. Now this is an interesting example, and we have some notes on this. But let me stress. Hold on. Let me stress that this is really an open problem. So we know a lot mathematically about instantons and the fluctuations around instants. We know embarrassingly little about the fluctuations around these non-BPS solutions. So Karen Uhlenbeck proved their existence even in SU2. Okay? And in CPN, you can write all of them down in closed form. But absolutely nothing is known, as far as I can tell, even about counting the number of negative modes, except in extremely symmetric examples. Okay? So this is a very, very difficult problem.
But these are instanton anti-instanton.
They're not instanton anti-instanton. They're saddle points.
Yeah, but they saddle points in the sense that they have basically a stable mode.
Right, but
Okay.
I think this is partly semantics. Just think of them as classical solutions to the second-order equations. You don't even have to say the word instanton. They're classical solutions with finite action. Okay? What you want to call them after that is they play the role of instanton anti-instantons in this sense, but you don't need to call them that. So there are, yeah, it's simple to write explicit solutions, but not all of them. In Yang-Mills, yes. Yes, I can show you some afterwards. Very simple. All right, I'm going to have to skip this because it's also covered by other talks in this workshop. But let me just mention that one of the overlap ideas in this workshop is that suppose you want to now probe this question of whether resurgence is useful or interesting or applicable to quantum field theory, rather than starting with something very difficult like Yang-Mills, you might think that a more logical place to start is with some localizable quantum field theories, which have some symmetry of their manifold and their field space and some supersymmetry, where actually the functional integral can be reduced, localized, to something a little bit simpler, to ordinary integrals, but many of them, matrix integrals. Now you're in a regime where you can actually really do something in terms of asymptotics. Not just formally, you can really do calculation. There's some beautiful work by various people, some of whom are here. Marcos Mourinho, Ricardo Schiappa talked yesterday. Ines will talk later in the week about some of these examples. So examples like 3D Chern-Simons on S3 or on some lens space. You can just do all this thing to death. You can study the Borel structure. You can look at ABJM models, which also localizes, and you can study the Borel analysis. You can just do everything in these things, partly numerically, partly analytically, and it really works. It really helps to organize the asymptotics. There are also examples on S4. There are some very, very nice examples for Wilson loops, which have expressions that now can be studied. They depend both on say, some level number n and some coupling. You can write it in terms of a Tuft coupling. You can study the asymptotics in both directions. There are all sorts of very interesting things that can be done and have been done. I want to spend a couple of minutes talking about a correspondence to this work that Sergey talked about this morning, there's this very beautiful, but to my mind still very mysterious, relation between ordinary differential equations and integrable models, which are themselves related to interesting conformal field theories, and even deformations of conformal field theories. And the story, I think, is this beautiful observation of Patrick Dorey and Roberto Tateo, building on work of Andrei Voros, who'll talk tomorrow, right, about some of this, that a fairly innocent-looking Schrödinger equation with some spectrum, m is some number, okay? So if you try to study this using in the complex plane, there are of course Stokes wedges, depending on the value of m, and you have to do this whole Stokes analysis and patching things together. And if you do that using these techniques that Voros developed, you can find exact functional relations for the spectral determinants. So these are for the odd or even modes for this potential. And what Patrick and Roberto pointed out is that this is basically the same thing as had been discovered in the conformal field theory context by various people, but Bazhanov, Lukyanov, and Zemolodchikov, for some certain expectation values of operators in conformal field theory satisfy what's called a quantum Wronskian condition, and that these are the same formulas. Okay? This is actually made even deeper because this was, say, just for, say, a ground state, but you can add an extra degree of freedom for excited states, and this generalized potential here, think of some sort of radial 1 over r squared thing here, and the spectrum for this is directly related to the, there are certain operators in this conformal field theory, their expectation values just map exactly to these spectral determinants in the quantum mechanics problem. Another way of saying it is that the monodromy problems for the Stokes analysis of these Schrödinger equations encode somehow the complicated TQ relations of Baxter for the corresponding integral models of conformal field theories. So to my mind, this is spectacular. This is extremely interesting. And it's a way where Resurgence could actually contribute something significant to some interesting quantum field theories. Because, as I said, a lot of the Resurgence work by mathematicians is developed on the ODE side. Okay? But now in the last, okay. Oh, wait, I'm an organizer, so I can take as long as I want, right? So I'll just lock the doors here. So I want to discuss this a little bit. A really important physics question is, can you get some information about strong coupling from weak coupling, and vice versa? So generic behavior in many cases is that weak coupling perturbation theory might give you an asymptotic divergent series, whereas strong coupling gives you some convergent series. What's the relation between these two? Is there some relation? I mean quantitative relation. If I give you some expansion here, I want you to then tell me the expansion over here, and vice versa. So how can we even answer this? And I want to pose this as a question even in a problem where the degrees of freedom reorganize themselves in complicated ways in the weak coupling or strong coupling regime. So the dream is QCD. Short distances, asymptotic freedom, quarks and gluon degrees of freedom. Long distance, confinement, pions, protons, blah, blah, blah. Totally different degrees of freedom, right? So that's the dream. Of course, I don't have a solution, or I would be talking about that solution, right? But let's try and probe this question in some simpler models where we can actually do something. Okay, so clearly ordinary asymptotics is not going to be enough, but maybe Resurgence can get you closer to an answer. So I want to talk now a little bit about this Matthew problem. We heard about the Matthew problem and the modified Matthew problem this morning. It's extremely rich, surprisingly rich. So this is just a periodic potential problem. Let's call the eigenvalue U. There's some potential, and I'm writing it like a physicist. I'm putting in h bar. So the energy, the bottom of the potential is at -1. So the energy is -1 plus the harmonic oscillator term plus the expansion. So this is perturbation theory in h bar, what I was formerly calling G or G squared, okay, for the level number n. Now you should have objected because this can't be the whole story. because clearly if n is of order 1 over h bar, this doesn't make sense. Okay? And that corresponds to the level being basically near the top of the barrier. So really you should view this energy not as a function of one variable h bar, but as a function of two variables, n and h bar. And I claim that this is a very, very precise analog. A lot of the large N physics in matrix models, all these localizable field theories. So let me show you how that works. So first of all, let's look at a picture. This is the spectrum as a function of h bar. You see the bottom of the potential at -1, the top of the potential at 1. You see deep down in the potential, there are exponentially narrow bands, as we expect. And the bands start at -1 are linear in h bar to start with. Way up above the top of the potential, there are exponentially narrow gaps. It's basically a free problem, but with very narrow gaps. And near the top of the barrier, these narrow gaps turn into wide gaps, and then the wide bands turn into narrow bands. So how does this transition happen? And in solid-state physics language, you describe this problem using the, what's it called? Brillouin zone, but these atomic, basically localized atomic levels. Yeah, okay, thank you. So, whereas up here, they're basically free particles. Okay, so the degrees of freedom completely reorganize themselves in some complicated way as you cross this point. So how can you do this smoothly, uniformly everywhere? So let's look, here's the expansion that I just showed you, but you can look at the expansion at large n. And this is also known, and we saw this formula this morning, but for the modified Matthew equation, here it is for the Matthew equation, expansion 1 over h bar. So how are these two things related to one another? All right, so let me look more closely at the large n. Here it is. Turns out to be useful to define this so-called Tuft parameter, which is n times h bar over 2. It's the classical action in this limit. And then you can reorganize this expansion as an expansion in large A, or large Tuft parameter, also in h bar. Okay, it's just juggling these things. You see you've got a 1 over n squared. That becomes this 1 over a squared, et cetera, et cetera. Now the connection with the rest of this workshop is this object here is directly related to Nikita's partition function in a very concrete way. What is that? So these n equals 2 supersymmetric theories are specialized to SU2 is described by some moduli parameter. There are 3 distinct physical regions called the electric, magnetic, and ionic region. The basic things entering this prepotential are the scalar, expectation value, and the dual scalar, and they're related this way through the prepotential. And the prepotential has these interesting expansions. The relation to the Matthew problem is that if I rewrite the Matthew problem like this and define A to be this A that I just defined, then this eigenvalue is exactly given by the derivative of this. Okay? It's just the same problem. Okay? All right, but this expansion I gave you here was in this electric region where A is large. I should be able to describe this everywhere. And so the way to do that was pointed out by Mironov and Morozov, is that you just do all orders WKB, which was discovered long, long ago by Dunne. You just have an infinite expansion. The integrals get more and more complicated as you go up, but you can do them. For this case, they just all give you hypergeometric functions of some sort. This gives you A, this WKB action as a series in h bar squared with some complicated functions of energy. At large U, way up in this electric sector, you just expand these and then invert. You invert and then you get U as a function of h bar and A, which you can think of as U as a function of n and h bar. Okay? So that's how you use U all orders WKB to generate these eigenvalues. And then you can just check that the thing that you generate this way is related to this prepotential. But this is explicitly now in the electric region. So now I can give you this 2-line proof of this relation that Mittad and I found between the instanton fluctuation and perturbation fluctuation. It turns out this prepotential language is just exactly the right language to phrase this question. And it goes like this. Remember, Zinjastin and company found that there were 2 functions needed to generate the trans series. I'll call them B. B is basically n plus a half. N is the level number. and A, exponential of A is this fluctuation around the single instanton. So we noticed that there was this very simple relation between the derivatives of U with respect to the level number and the derivative of this A with respect to the coupling, such that if I know one, I can write down the other in one line. Now here's the proof. From this prepotential language, U was some scale derivative of the prepotential. Let me differentiate this formula with respect to A, little a. On the right-hand side, I just get A dual. Lambda, remember lambda squared was the coefficient of the cosine, so that's basically 1 over h bar. So this is basically a derivative with respect to h bar here. And the identification is that A, this WKB guy, is just n plus a half. It's just the level number, the action. And this A dual is essentially this capital A thing plus a shift. Right? So it's just encoded in these action integrals, which are themselves duals to one another through this prepotential. So it's literally a two-line proof. And it's amazing that nobody ever noticed this before about ordinary WKB. Right? It's quite surprising. It's a very deep observation about WKB, saying that you don't need to calculate all orders of the tunneling guys. They're encoded in the all orders of the Bohr-Sommerfeld. Okay?
That's the meaning, correct?
It's a natural way to describe it and to derive it. Let me say that. Okay, I'm really running out of time, so let me just say that this Matthew equation corresponds to what we call n equals 2 supersymmetric theories. N equals 2 star are encoded the same way in the Lamé equation. Details are a little bit more complicated, but it's basically the same structure. And thinking of this Tupf parameter being small, down here, here, or here, actually corresponds to the dionic, magnetic, or electric sector. So remember, in the quantum mechanics language, we're sort of changing degrees of freedom from these localized Wannier states to these delocalized scattering states, and something very complicated is happening near the top of the barrier, some very complicated redistribution. And we see that this is in one-to-one correspondence to how the fields in these supersymmetric theories are redistributing and reorganizing themselves. So it's not Yang-Mills or QCD, but it's something like that. Okay, I've really run out of time, so let me just skip through this. Let me just show you one more picture, is that right at the barrier top, the widths of the bands and the gaps are equal. You can see this already, that this width here is equal to this width is equal to this width, and they're of order 1. They're not exponentially small. And using this resurgent analysis, you can do this smoothly, all the way across, okay? And describe everything uniformly across the top of the barrier. All right, I'm going to have to skip this, I'm afraid, and come to the end. So let me conclude. So summarize, the basic idea of resurgence is that if you're able to combine perturbative analysis and non-perturbative analysis in some systematic way, I hope I've shown you enough examples that there is the potential to learn something about one sector from another sector, and not just something, really concrete information, explicit information. And these trans series that you build really encode a lot more information that you would just get from perturbation theory. And that so the applications that have been studied so far include matrix models, large N, strings, and we'll hear talks about these in this workshop. I talked about the infrared renormalon puzzle resolution in CPN models, the fact that you can generate all of multi-instanton physics directly from perturbation theory, relation to these n equals 2 and n equals 2 star. And one thing I'm particularly interested in at the moment is trying to understand this in the language of this ODE integrable model correspondence that Sergey told us about this morning, even elevates beyond this to really non-trivial quantum field theories. It's extremely beautiful work, and I think this is somewhere where resurgence could actually do something very concrete. And I think underlying this whole story are these basic statements that if we think in path integral language, we really should be thinking in terms of doing steepest descent calculations, expansions properly, and in terms of analytic continuation. So, thank you.
questions? Okay, with
I went
the
to.
beginning of the workshop, I think we'll encourage everybody to go to the rest of the talks. Thank you.
Yeah, sorry.